Hello everyone, welcome to another video in the bare metal assembly programming series that is specifically targeting the Raspberry Pi 4. Now if you've ordered a Raspberry Pi 4 and it hasn't arrived yet, you can still follow along in this tutorial because we will not actually be writing Raspberry Pi 4 specific code. It's going to be for ARM assembly. The reason we're doing that is there is some principles that we need to cover before we can move forward. And those are registers and conditionals, or if statements, as it were. Now, as a side benefit, we will actually also be covering while loops and for loops, because a while loop is easy enough to make, and a for loop is just a while loop with a conditional in it. So it seems like all these things should work together pretty nicely with one another. If we go to our code, you can see I've added some comments to the top here. These comments say that it's designed for the Raspberry Pi 4, and it is. There's specific code here, I guess, for that. Our processor is a Cortex A72. I also included some documentation, or a link to the documentation on the ARM instruction set, and we will be using that today. So first off, registers. What are they? Well, a register it's like a global variable. I remember when I first started programming, I used global variables and they were great. They're at the top of the code, they always exist, but they start to become a little cumbersome. You have to remember, is that value in there still useful, or should it be thrown away? Things like that. And then scoped variables become a lot nicer because you don't have to keep in your head every single thing, keep it straight, and all of that. Well, with assembly programming, we're basically having global variables again. We're back to using global variables. Now, you might be wondering, why would we go back to using global variables? Well, it comes down to circuitry. Inside the ARM processor, there's a whole bunch of little wires, and like literally microscopic wires. But there's also a bunch of switches in there as well. So we can't have an infinite number of circuits inside of our ARM processor. If anything, it's a reduced instruction set. So our goal is to try to make it as simple as possible in a lot of ways. So let's think of a real life example. Let's say you're looking at your car and you want to wash the windshield. So you flip the little switch inside the car and windshield wash will come out of the reservoir and it will spray up on your windshield and the wipers will go back and forth and then the windshield is clean. Well, that reservoir is kind of like a register. That it holds something that we need to use for the operation. Our operation of washing the windshield requires the windshield wash, which is held in the reservoir. When we want to add numbers together, we need a number in a very specific spot to work with, and it's like a reservoir, or it's called a register. It holds our number to perform the operation. Now I could put 10-gallon jugs in the trunk, and every time I run the wash operation, it never will take wash out of one of those jugs in the trunk. It will always come from the reservoir. And just like when we perform an operation, it will not take a number out of the RAM, no matter how many RAM addresses we have access to. It will never come out of the RAM. It'll always come out of the register. So you can see just how the reservoir in a car is hard coded or hardwired, I guess you could say, into the washing operation. A register will be hard coded into our programming operation that we're working with. So the first command, let's cover the move command. So if we go to the documentation, under the instructions, and we will look at move. So what it says is that we can move an immediate value into a register. Now you'll notice there's W registers and X registers. Well, just like global variables, they are used globally, which makes sense. But as we talked about with circuitry, we don't have an infinite number of circuits. So we have a limited number of global variables, you could say. And you might be wondering, how many do we have access to? Well, if we look at the documentation, it says that we have x0 through x30. Now, if you did 32-bit programming, you'll remember that you had R0 through I believe it was 15. R stood for register, and then the number after it was which one you wanted to work with. Pretty nice naming convention. So why is it now X? Well, X, I'm assuming, stands for extended, because there's 64 bits now instead of 32. And you can see we also have the W registers that only hold 32-bit. And you might be wondering, well, so if X is extended, where does W come from? And I'm guessing W comes from, it's the letter before X. That's my guess. There might be another reason why, but I'm guessing it's because it's the letter before X. All right, so if we have 0 to 30, it would be 31. Do we have 62 registers to work with? That'd be pretty cool. No, we don't. So let's go back to our code window a little bit here. We know that there are 8 bits in a byte, and we can represent a nibble, which is half of a byte, with a hexadecimal character. So this would be 4 bytes, and that would be 32 bits. And let's do 1, 2, 3, 4, 5, 6, 7, 8. This would be another 4 bytes, all set to 0 though. So this would be 64 bits. If we were to say that x0 equaled this number, we could hold it all. However, W also occupies the same spot in the circuit, essentially, that X does. It's just that it only can work with the lower part. It can't access these higher numbers, I guess you could say. So do we have 62 registers? No, we only have 31. The X's and the W's overlap with one another. All right, so we've talked about how registers are hard-coded values for an operation to proceed, just like the wash reservoir. We've talked about how many of them that we have, and we briefly looked at the move instruction. Let's actually try it though. Let's see what happens. Now, we're not going to get into the weeds. There are some limitations the way the ARM processor works, but we're going to keep it more of high level, I guess you could say. So if we want to save the value 1, 2, 3, 4 into x0, it would look like this in other languages. This is how we would do that task. We would say we want to move 1, 2, 3, 4 into register x0. I will save this, and just to prove that it compiles, you can see I've already put FASM ARM into my folder, and you can see I've even already done a build in the past to confirm that what I'm doing makes sense. It's always good to do that. So what I'll do is run FASM ARM and then boot S, and I want my output file to be called kernel8.img. You can see that it compiled. It's a total of 4 bytes, and if I do open with hex editor, now you might not have that. I should point that out. If you want it, you can search for the extension hex editor. It's made by Microsoft. Anyway, we can see that we have 4 bytes. This is what all of this turns into these 4 bytes. Now, there are some limitations because there's only 4 bytes, but we won't get into that for now. it'll accomplish what we need. When we get to that point where that limitation is apparent, then we'll discuss it. But let's say we think we got this all figured out. Let's say we want to add 1, 2, 3, 4 and 2, 3, 4, 5. Can we do this? This would be the same as x0, 1, 2, 3, 4 plus 2, 3, 4, 5, right? Well, let's save that and see what happens. If you hit the up arrow, it allows you to run the previous command. Yells at us. The second parameter is invalid. What do we do wrong? Well, let's take a look. If we look at the add instruction, we can see that there's this one. So there's our destination, XD for destination. And then we have a register and another register. Well, that doesn't help us. Oh, immediate. There we go. We have a destination register. That makes sense. A register and a number. And while we're here, also all the numbers seem to start with pound signs. Well, yes, they should. The nice thing about FASM is it knows what a number is, but we are going to try to remember to add pound signs, because if we want to compile this on a different assembler, we want it to still work and not just get a whole bunch of errors saying the pound signs are missing. Did that fix our problem, though? Nope. Still not happy. Okay. Well, oh yeah, that's right. Even though it says immediate, which is an immediate value, there's still a register involved. This goes back to what we were saying before about there are hard-coded circuits that expect certain things. And these are the only 3 ways to add. You can add with 2 registers, or you can add with 1 register and an immediate value, or 2 registers, again, with a shifted value. So we're limited on what we can actually do, but we can fix this because we know that 1, 2, 3, 4 happens to be in x0 to start out with. So will this work? And the answer is yes. There we go. So we have successfully saved a value into a register, and we've been able to add them together. And I think that's probably good enough for registers for now. You kind of have a grasp of what they are and why they exist and why we use them. So let's move on to a while loop. So we'll put this in here. And this is not valid code. It is for BASIC. It is for BASIC, but not for ARM assembly. But I think it helps explain what we're looking at. When you put in a word with a colon after it, it means to basically bookmark this address location. Now this is why org is so important for our origin, because if it assumes 0, even though our code is placed at 80,000 hexadecimal, when we say go to this location, what it will do is it will go to this one, which is the wrong spot. We don't want this code to run. However, when we add this origin like we have it, the assembler knows that this loop word, or label I should say, is located at this address, and this makes sense. It will be able to run this, and we've just created a while true loop. It will run this forever, but this is not the right instruction, so what is? Well, on x86 it would be JMP for jump, but it's not that either. We use branch. So we have marked our current spot in memory, which happens to be 80,000, and we're saying that we want to do this logic, and then we want to branch back up to this address. But we don't need to keep track of the addresses because the assembler does it for us. That's the benefit of using assembler and not writing out hex by hand. So we have an infinite while loop. It will run this forever. But we also wanted to talk a little bit about for loops because they use conditionals. So let's do that. Let's imagine that we had this for loop, x equals 0, and while x is less than 999, x plus plus. I would say this is probably a fairly common type of code that you would run into, where you create a value called x, set it equal to 0, and you say as long as x is less than 999, then run through my loop, and then when you're done, add 1 to x. So then x is 1, and you run through it again because it's still less than 999. Well, let's call x x0, and let's write an assembly equivalent to this. So if we move into x0 the value of 0, now there's another way to do that, but we'll do it this way for clarity. Then we have our loop that we want to work with, and we will run through all of our code, and then we will introduce a new instruction, and that instruction is the compare instruction. So how does that work? You can see documentation is your friend. So what it says is that we need to pass in a register. As expected, we can pass an immediate value, and it says the way it works is it subtracts an immediate value from the register. And you might be thinking, okay, so in our example, it will take, we'll say x0, 0. Oh, I take that back. 999. That's our goal we're looking at. So it will take whatever number we have, subtract 999. Where will it save it? And it will discard the result. Well, that seems kind of useless. But it's not, because what it does is it updates the condition flags based on that result. So what are these condition flags? Well, surprise, surprise, they're in a register somewhere because the circuitry needs to be able to use them. But these are the flags that we'll be working with. Specifically, the one that we care about is the 0 flag. Now, what will happen is we will take our number, we'll start with 0, minus 999, and we'll say, is that 0? And the way we do that is we say, was the 0 flag set for us? And if it's 0, that means that they were equal, right? Because if this was 999 minus 999 gives us 0, that's the only number that will ever give us 0, so they must be equal. So we'll put in here branch, in this case, not equal. Go back to loop. So let's think about, let's first make sure it compiles so that I'm not just, yep, it compiles. So the way this works right now is we put 0 into x0, and then we're doing a bunch of logic, and we're saying 0 minus 999, is that 0? And we're saying nope. So branch, if it is not equal, which they're not, go back up to loop. So what we've done then is we've added a condition to break us out of the loop. If this is 999, 999 minus 999 gives us 0. Branch, if it's not equal, well, it is equal. It is 0. It will not loop. It will go to the next line of code, whatever that code may be. So we have talked about for loops, and we've just barely touched conditionals. So the only other thing that I really want to touch on conditionals is we'll get rid of the loop aspect of this, just to focus on the conditional. So we know how not equals works. This is based on if x0 doesn't equal whatever number we supply, or it could be a register. But in this example, it's an immediate value. I need to remember to include the pound signs. FASM is very forgiving with that. What else is there? Well, there is equal. So we can put that in here. That would be x0 equals that, then jump to a label that we actually have somewhere. There is less than. There is less than or equal to. There is greater than. And there is greater than or equal to. All right, well, that's really all that I wanted to cover on conditionals, because we will be using them in the next video. So what we've covered in this video is we've talked about registers, we've talked about while loops, for loops, and conditionals. Really, these were the two things we want to talk about, and these looping ideas came along for the ride. But I hope you found this video enjoyable and educational, and that I think that's all that I really have to say. So I look forward to seeing you in the next video.